of general relativity. And people know it was born around 1915 at the hands of David Hilbert and Albert Einstein. Okay? So, and what happens? This theory got experimentally verified 70 years before it was born. How? The famous French astronomer Leverrier, he experimentally measured very accurately the advance of perihelion of Mercury, which is per century, 43 arc seconds per century. So what is the advance of perihelion? I always remember my best friends are my students. Many of them are there, but being little bit senior in age, all of you could be as good as my students. So Leverrier measured experimentally. He was an astronomer in 1845. Now, our Earth revolves around the Sun. It takes 365 days approximately. Now, so you can just in an elliptical orbit, so you have major axis and minor axis. Now, after 365 days, when it comes back, it does not come back to its original position, but this axis gets rotated by a small amount. This is called as advance of perihelion. But for Earth, the ellipse is not so skewed, and so it's not so much appreciable. However, Mercury is the tiniest planet in our solar system, and its elliptical orbit is little more skewed. Okay, so this is something worth talking. So advance of perihelion of Mercury. The same thing will happen to any object which is revolving around some other object, some other star or whatever. So general relativity got experimentally verified 70 years before it was born. This is a very important point. Now, particularly in the last 1 decade or 1.5 decade, we have many milestones, landmarks in this direction of gravity that have always hit the headlines, newspaper headlines. So, detection of gravitational waves at LIGO, the mapping of the image of the black hole, supermassive black hole, Professor Sankey just now mentioned. So, a supermassive black hole is sitting at the center of a galaxy called as a distant galaxy called M87. It is so big and so huge that its spread is something like 40 billion kilometers. It's larger than the size of our solar system. And it's 6 to 7 billion times heavier than our solar mass, or mass of the solar system, because all other masses are negligible as compared to the mass of the sun. So you can say mass of the sun or solar mass or whatever you like. Okay, 6 to 7 billion times heavier than that. And an array of 8 telescopes spread across the globe. So you need all kind of people, computer man, this man, that, all branches, and from the entire world. So they are called event horizon telescopes. So I would explain to you what is an event horizon. So for a black hole, some imaginary surface around a black hole from which nothing can escape. I'll come to it little in a couple of minutes. So this mapping of this supermassive black hole taken by this array of event horizon telescopes, and this has been very, and it was so bright, maybe brighter than the brightness of the entire set of stars in the galaxy. Very intensely bright ring of light. So now advance of perihelion, so it's not only a textbook material. You can calculate it also in non-relativistic classical mechanics, but you can also calculate it in general relativity. Now, the physics Nobel went to, in 2020, it went to a set of 3 people, Roger Penrose, and I happened to meet him twice at Delhi, heard his talk, brilliant talks. We need to talk separately perhaps on that. And the woman, Andrea Gage, this woman physicist worked on, Roger Penrose gave the idea that there is a supermassive black hole also at the center of our own galaxy. And it's sitting at the location Sagittarius A star, SD A star. So obviously thousands or lakhs of objects may be revolving around it. Andrea Gage identified one such object which is called as star SO2 or S2. And it takes around little more than 16 years to make one revolution around this supermassive black hole sitting at the center of our own Milky Way galaxy. This woman physicist kept tracking this guy for more than 16 years to accurately measure, and this is supposed to be the super test of general relativity and the most recent and the super test of experimental verification of general relativity. And for some of my female colleagues sitting here, I would tell you that you please look into the story of this woman, Andrea Gage. She was a professor at Chicago. She only had the title and did not have the salary for almost 40 years. Please read these stories. But she never gave up. Her husband was also a professor, but she did not give up and she kept doing this. Now she is a full professor in Los Angeles at some place. So, I mean, it's a sad story on that part, but it doesn't matter. So, this is what I want to tell to my female friends and colleagues. Never give up. Don't worry about if you can survive. Do what you like most. Okay? Don't give up your dreams. So, this is, these points I wanted to recap. I think everybody knows these things, but still it was worthwhile to recap them to a nice audience like the ones we are having here. Okay? So then one would think that if general relativity is so nice, so elegant, so successful, why do you still worry? Why can't you have your dinner and sleep? Okay, peacefully. But it doesn't work like that. Okay? Your mind is curious, you want to know. So there is an important, everybody knows about the Big Bang. As I said at the beginning, the universe was born 13.7 years ago. So everybody knows that Big Bang took place 13.7 billion years. So Big Bang is a singularity. So if you run the universe backwards in time, you hit upon a singularity called as the Big Bang. Okay? And somewhere around that time, your general relativity would break down, it will no longer work. So those are the Planckian scales. The Planckian time is 10 to the power minus 43 seconds or something like that. Planckian energy is 10 to the power 19 GeV, and Planckian length scale 10 to the power minus 33 centimeters. So your well-known theories of gravity would break down, no longer work on that at such singularities. What singularity is? Black hole itself is a singularity. Let me first take 2 minutes to explain what is a black hole. Okay, so my talk is never a research talk. It's always also full with simple ideas for the youngest students. So we all know escape velocity. We do it in first year, right? Escape velocity of Earth, you give it by square root of 2 mg by r, right? So now, or r square, 2 mg by r, okay, dimensionally. So B is on this side. Now, if I keep the mass m fixed, and if I keep reducing the radius r. M is the mass of the object Earth and r is the radius of the Earth at the moment. Now I keep my M fixed and I reduce the radius. So to say, we squeeze this auditorium from all sides in a compact tiny space. So what happens? As you increase, M remains fixed, you reduce R. You don't increase, you reduce R. So R is reduced. And when it reaches, when you reduce R, escape velocity keeps increasing. Okay, for Earth it may be 11 something centimeters per second or whatever. Now, when the radius of the Earth becomes 8.43 millimeter, the Earth becomes a black hole. Why? Because the escape velocity now becomes identically equal to the velocity of light, or the whatever natural velocity which is maximum attainable velocity in nature. So that is at that moment my Earth becomes a black hole. If I do the same thing for my sun, the star, then it would be something like 3 kilometers. Then sun would become a black hole. So it's very simple. And I then introduced the idea of event horizon, that let there be an imaginary surface around this black hole, which cannot be escaped even by light, so that everything is being trapped inside, and therefore you call it a black hole. Now this is a simple idea. So this is an illustration of